Hello, everyone. It's my pleasure to welcome all of you for our second QRE talk. And today we have folks from Zapata and especially Amara, who will be talking about, the paper about early fault tolerance they have recently put on archive. And later we have some discussion and a panel discussion. So that's great. I don't think I have any particular announcements this time. One thing I wanted to say is that I wanted to say thank you to Shui, who has been helping me organize this event and will help me organize future events. So that's great that we got some people involved. So thanks a lot for that. And she's been pretty active on the Discord as well. If anyone here is not on our Discord and would like to be there, let me know and I will send you a kind of invite link, or we'll post it in the Zoom chat. For people watching that on YouTube, just contact me and I will send you an invite link. And now, without further ado, I will give it to Amara. Amara.
Thank you. Can you all hear me?
Yep.
Okay. I apologize. I sound a bit sick because I've been sick for the past few days, but I should be okay. And let me share my screen. Okay. All right. So this is going to be a talk about what's being called early fault-tolerant quantum computing. I'm a research scientist at Zapata, and this is not confidential, so ignore that thing. So I did not work on this alone. I had people to think with. We thought together. So my collaborators are Katerina, who is a research intern at Zapata, Peter Johnson, who is the head of the research team in algorithms, and Athena, who is a software engineer and research scientist at Zapata. Okay, just give a moment. So the outline of the talk, the different sections, will be, I'll try to set up the drama and argue why we are at a critical point, a critical stage in quantum computing. Okay? And this drama is going to be heightened by the fact that through the logic of the field, the inevitable evolution of the field, there are two cultures in quantum computing that have come up. And the emergence of these two cultures is their attitude toward error correction. And from the emergence of these two cultures and the attitudes toward error correction, I'll try to motivate this idea of early fault tolerance. And then we'll talk about early fault tolerance as a concept in and of itself, distinct from the other two kinds of computing we've heard about. So that's the outline of the talk. So let's start with a rather simple and important question for the whole field is, will quantum computers be useful? Okay. Now, if you're a student or a professor or an academic, the answer is simple, right? You just go to the Quantum Algorithm Zoo. There's a list of algorithms that you can choose and see the speed ups. And if you're ambitious, you want to add your own to that list. It's straightforward. If you're in the industry or you're interested in something more practical, you shoot for something higher, then the quantum community has a party line. Right? The party line is that, yes, we could do something useful. Right? And here are just a few examples in drug discovery, cybersecurity, mathematical modeling, and these sort of stem from the fact that quantum computers are supposed to be, a bit more efficient at studying quantum systems. We know how to we're beginning to learn how to better, solve differential equations. We have encryption schemes. So, in the high in the sky, there are these things that we can say we're going to be useful for. All right. But then there's a section of us that, try to cross the T's and dot the I's, right? And the way what they do is they ask very careful questions about, well, what does it really take, right? And over the past couple of years, we've been asking very pointed questions and asking very sober questions. So one of the papers that I would like to point your attention to is this paper that came out last year. So this is very recent. And it was mostly considering what it takes to upload classical data onto some quantum computer. And okay, so there is this fact that these operations in a quantum computer are like slower than classical operations. So you might think this might affect the computation. And essentially what they tell us is that, supergraduate speedups are needed, right? And they say, if you want something where you're almost promised some speed up, look to chemistry. There's more hope there. So then you look to the quantum chemists and ask them, what are the chances of a quantum advantage? What are the chances of quantum computers being useful? And so again, question asked, question answered, at least a portion of it. And what you see is another sentence I would like to highlight, which is, we conclude that the evidence of such an exponential advantage across chemical space has yet to be found. So it's not as simple as we'd like to think. The question is a bit more delicate. And if you look to the people who have hundreds of millions of dollars to invest in academic institutions and industry, and then you ask them, what do you think about this architecture, this new model of computation? Well, this is an article from CNBC. And they say, every few years we look at quantum computing. It's a very interesting quantum project. But, for whatever we're doing at AI, at Meta, it's not really useful. And they decided a decade ago that AI was the way to go. And in some sense, at least for now, they were justified, right? So this sort of, these results that are causing us to proceed with a bit more caution come from people, trying to do really sober estimates. And we're going to need more of these as we develop quantum algorithms and really try to put our quantum algorithms to the test in sort of practical utility cases, right? So the question is, as we move forward and as quantum computers improve, are we in a position to do this, to get the sober estimates? Okay. And there's a problem, at least a problem, something I think is a problem, is that two cultures have emerged, okay? And each have their own distinct answers to this question and a distinct strategy to answering this question. So there's like some useful quantum computation, whatever it is. I'd say at this point, we don't really know. One community is the NIST computing, okay? They're resigned to the existence of errors. And the whole point is that we're going to try to eke out as much coherence and quantum juice as we can. We're going to try to make sure that our computations are not small enough so that they can be simulated, not too noisy so that they can also be simulated. So we have a QPU that's big enough, current enough, that you can't simulate it. And then there's some application out there that will give us the quantum advantage. Then there's a fault-tolerant quantum community, right? And those, for the most part, assume an effectively perfect device, and they assume that you can do arbitrarily long computations. Okay? And how they approach resource estimation, so how the question of resource estimation is talked about and where if a computation will occur is very much answered from the starting points of each community. And I would say, near the twain meet. So the question is that, are these the only two paths? In fact, as computers get better and better, is it useful to just to have these two options? Okay, are these the only two options? And I think the answer in our work, we say the answer is no. These are not the only two options. And I'll try to argue why it's useful to have a third option. One, I'm going to try to argue that it's necessary. And in fact, if we want to look for useful computation, a third option will be much more useful to have. So what is the third choice? So there's a huge claim that we all hope in some sense is true, right? we all know fault tolerance is sort of needed for arbitrary long computations. And so at least some of us are resigned to the fact that we need some kind of fault-tolerant protocols that we need to implement. On the other hand, as devices improve, right, we don't want to wait 60, 50 years for the best kind of quantum computer. We're going to have to allow some kind of error, right, in the computation. And the hope is that in this regime where you can do some fault-tolerant protocols and allow for some error, that's where the first useful computation will occur, right? You want to relax assumption somehow. And so this is the crucial point, right? This great claim, this great hope is not really adequately addressed by either community. The NIST community is such an assumption that you aren't great enough to do error correction, or too small enough, too small to do error correction. On the other hand, the fault-tolerant community, right, is trying to avoid discussion of errors. Right? Everything is fault-tolerant, nearly perfect. And if we're going to have useful computation, each community is going to have to sort of give up something. And so the billion-dollar question, literally, is that this useful computation, chances are it will happen in the transition period between the NISC community and the fault-tolerant final community. And what we'd like to do, what we'd like to answer is, how do we characterize this transition period, right? How do we quantify this great claim, this hope, and show how you can cash it out? Right. So this is the transition period, I think, is where all the juice is going to be happening for the first useful computation. So in order to get an idea as to how this transition would look like, the strategy we're going to follow is we're going to follow our nose and see the kind of logic that we usually follow to argue that we can do fault-tolerant quantum computation, and see what kind of breaks down in the transition period, and then start from there. So roughly, there are 4 steps. I'm simplifying things, of course, but you're a hardware person, you're an experimentalist, there's a certain amount of work you need to do to make, let's say, gates. You make qubits, you make gates, it takes a certain amount of work. And you're going to assume that it's some effort that you can quantify, and it's constant over all scales. Scales being the size of the QPU. Okay, you can construct these gates, and you need to do error correction. So you have these gadgets that you can make bigger, or you can concatenate them, right? And the hope is that if you do well enough with the errors, right, you have to be below some threshold. And the reason that you have to be below some threshold is because error correction introduces some redundancy. So you're going to have to do more operations to introduce the redundancy. So naively, if you're not too careful, error correction just adds more errors, right? So you need to be below a threshold so that error correction corrects more errors than it introduces. And once you have that going, right, this is the underlying assumption of the threshold theorems, right? They show that if there's some threshold that you can get to, error correction takes over, you get exponential reduction in errors with a polynomial amount of effort. Okay, so that's sort of the story of the whole field. Now, for those who pay attention to hardware, you should be saying, well, aren't we already at threshold in a lot of platforms, right? I mean, can we make good gates? So there's something weird about that story, right? And in fact, we can. This is 2014, when I was in grad school. This is the USCSP group, right? And so what I'd like to show you is the highlighted portion. Already a decade ago, we could get really good single qubit gates and really good 2-qubit gates, right? So the question sentence for me here is, this places Josephson quantum computing at the fault tolerance threshold for surface code error correction. Okay, so what's wrong with my early story? We are at threshold. Why don't we just scale up to tens of thousands of qubits and 100 millions of qubits and get it ready with error correction? Okay. So what's stopping us scaling up, right? The problem is that they're scale-dependent errors. it has to be the case, right? If I can get a threshold for 1 qubit and I can't scale up very easily, it must be the case that some part of the engineering process is scale dependent. So I'm going to give you a few examples of how this scale dependent might show up. Okay, so let's take, for example, superconducting architectures. There's certain kinds of qubits you can make called fixed frequency qubits, right? So there's a fixed frequency between the 0 state and the 1 state. And okay, we can't make these qubits identical, so there'll be some differences in the qubits. They're not exact, identical with each other. So in frequency space, right, all these frequencies are populated, and the way you make gates is you want to target these frequencies somehow. Well, if you have more and more qubits in your chip, you have more and more of these frequencies, the frequency space occupied. So the need to address certain qubits, right, the accuracy and the difficulty gets more and more complicated as you have more and more qubits in your chip. That's one way a scale-dependent problem can arise. Another problem is like in ion traps, for example. You have ions in a trap, and so you have the internal states of the trap of the ion where you store your qubits, and you have the motional modes of the trap. And you want to sort of couple the internal states to some motional mode, but you could have unwanted couplings, right? So in order to move those unwanted couplings, that problem, again, gets more complicated as the trap gets bigger and bigger. You can also have problems like with a classical crosstalk, right? You have sending control lines to qubits, but you can have unwanted crosstalk between the things that you have to calibrate and remove these unwanted interactions. Again, that problem becomes more complicated as the chip becomes bigger. So the point here is that as you try to scale up, there's scale-dependent engineering problems, scale-dependent errors, which means that at a certain point, if you try to do error correction, right, because of how the errors increase as you try to scale up at a certain point in time, you'll have diminishing returns of error correction. Right? You can do error correction to a certain point. You can't do it forever. And so the crucial question for us, like what we're going to try to answer, is how do we model this? All right. So I want to emphasize that, for each platform, this is a very complicated question. You need to do a lot. You need to know about material science. You need to know about the quantum noise channels, right? And so to answer this question in detail is going to answer, you're going to need a lot of details for each kind of platform. But okay, we're not experimentalists, but we also would like a much more general framework that's independent of platform, that's very simple to understand and can be a guide to think about computation in this transition period. So we're just going to state this, right? So the simplest way to introduce or to model this transition is that you have some base rate for your gate error, and we're going to make it dependent on the number of qubits. It's going to have some power law dependence. Okay? If you quibble with this ansatz, you can choose your own. What we're interested in more here is the framework that we're using. So we shall state this ansatz and then follow its consequences. Now, S here is going to be a crucial thing for us, which I'll call scalability, and Q is number of qubits. Okay, so scalability here is the new concept that we're going to use to sort of investigate the transition period between the Niski people and the fault-tolerant people. So here's a graph. This is, again, the point of this graph is just to get a little bit more intuition as to what's happening here. Okay. So on the x-axis, you have the physical qubits. On the y-axis, you have error rates. And you can see that as the scalability, the S parameter increases, the error rate does not increase as much. So the way to think about scalability is that you go to Google or IBM or some IonQ and you ask them, make me a 10-qubit chip. So they make a 10-qubit chip. You look at their entangling gates. Make me a 20-qubit chip, 40, 50, 100, right? And you look at the just gate errors. And the claim is that as the chip gets bigger and bigger, right, there'll be a degradation in the error rates of the planning operations. And so you can just sort of plot that. So I want to emphasize that this sort of tries to model the engineering difficulties, the engineering things that you have to do at a specific point in time. Okay, and this scalability model is what we will try to model this transition period, and it will model this transition period by the waning of these scale-dependent errors. So the nirvana is you're in fault-tolerant quantum computing. You can just scale up. Everything is wonderful and nice, right? Nisky computing is the other opposite end, where scaling up is a huge deal. It's very hard to do. So here is data that Katerina did for us. And you can see that there is some scale dependence, right? And for IBM devices, it's like 1.75. So just to, okay, can I go back? Okay, I can't. But this is the scalability where, as you increase the number of physical qubits, the error is really increasing. Okay, so we're going to use the concepts of diminishing returns for error correction and these scale-dependent errors to then define what we mean by early fault tolerance, okay? This transition period where we have this diminishing returns of error correction and scale-dependent errors is what we'll call early fault-tolerant quantum computing. Right? So we have fault-tolerant in there because we're trying to do fault-tolerant protocols, but we can't do them forever because of the scale-dependent errors. Now, the next part of the talk is I'm going to try to sort of introduce early fault tolerance as a concept in and of itself. Okay, so here what we had to do is in the paper we use surface codes as our error correction setting, but again the analysis can be done for any error correction code. And so in error correction, there's relation between the physical error rate and the logical error rate. And in our case, we're going to replace that with the scalability model that we have. So again, x-axis, for the moment, just look at the graph. You have the logical qubits now. So we are assuming some error correction. And the y-axis, we have physical qubits. Okay, so we have here for the paper, we're dealing with surface codes, but it could be any other code. We don't care. And what people usually have is those dashed lines. You increase you can increase the logical qubits, and there's a natural relationship between the two. And what the scalability model tells you is that you can see that there's a diminishing returns of error correction. As you increase the number of logical qubits, at some point, it tells you actually it's better to reduce the code distance, right? And as you increase the scalability parameter, the graphs look more and more like what people assume in scale independent errors. So in this transition period, what this means is that for any computation that you want to do, they'll give it, even with fault-tolerant protocols, right? There'll be a maximum size problem that you can handle. And so the question is that are there some algorithms that are sort of tailored that try to anticipate this idea of this maximum size of circuit that you can deal with and try to minimize the depth, right? In order to sort of have helpful computation. So what I'm going to show is that this graph here is simply shows is a contour lines of the maximum physical qubits you can have. For the details of how this is calculated, you can look in the paper. The red line with the x dot is where we are with IBM. The x dot is one particular algorithm that we're going to have. So here, the importance is that this regime is okay. Of course, the boundaries are a bit blurred, but the importance here is that to define this early fault-tolerant regime, it's a combination of hardware, how good your hardware is, what error correction you have, but also for our purposes, what kinds of algorithms are suited for this regime. So the last part of our paper is that we investigate and we talk about these algorithms that are so-called early fault-tolerant algorithms. And in order for this regime to be a meaningful regime, right, it must be the case that not only do you have these algorithms that claim to be for this period, but in some sense that they are really tailored and can really push the device to do more, given its resources. And so there's a burgeoning field of these kind of algorithms where you sacrifice the depth, but you pay in the complexity of the samples you need to collect. Okay. And the question we answer in the paper is that, is this a trade-off worth making in the presence of noise? And we argue that in the presence of noise, these algorithms, and we investigated, for example, what we call RFE, but it should be true for other classes of algorithms, that they do extend the maximum size of the problem is the size that you can handle if you use these algorithms. And so this transition period is not only inevitable because of just hardware, just how the nature of hardware progress, but there are algorithms that can be specifically tailored to this transition period. And so this is a meaningful thing to talk about. It comes with its own challenges, it comes with its own algorithms, and it comes with its own logic. So I'm going to conclude here about approximately 5 minutes early. So the summary of this short talk is that I argued that there's going to be a transition period between the NISQ and the fault-tolerant quantum computing model. As it currently stands, neither community is really has the language, the intellectual framework to handle this transition period. But luckily enough, we can characterize this transition period with this idea of scalability. With this idea of scalability, it allowed us to quantify, it allows us to be able to quantify where we are in this transition period, with one limit being the NISQ community and the other limit being the early fault-tolerant community. And the scalability parameter also can be used to understand these, scalability model can be used to understand these and find a really good use for these early fault-tolerant quantum algorithms. And it really motivates and justifies their existence. And so we can make the question more quantitative. We can ask the early question that I gave earlier about resource estimation, is that in this transition period, which we are going to be going into, what is the minimum scalability that we need for the first useful quantum computation? And it would be really cool to see and get measurements from devices, right? They tell us we can have scalability X, Y, Z, with the hope that as scalability improves, you can begin to see error correction get better and better, and these algorithms get more and more useful. Thank you.
Thank you very much. I recently learned on some Zoom meeting that the way to virtually clap is actually do this with your hands. So round of applause. Thanks a lot, Amara. So we have about 10 minutes for questions before we get into kind of panel discussion. So do we have any questions? I think Tanush just asked something in the chat. So maybe that's a good place to start. Tanush, do you want to ask it live?
Sure. Hi, guys. So, like, I understand that it makes sense to talk about the final argument that you gave. Can you guys hear me?
Yeah, I think so.
Okay, yes. So it makes sense that like we should talk about algorithms that can trade the coherent circuit size that you want to execute with the number of samples, and therefore, like potentially some of the early devices that we will have can deal with bigger problem sizes. But it's not clear to me, like, how, like, what's the argument behind the scalability model? I mean, I guess, like, is it just to say that like you will have, so yeah, I mean, it's like it's not clear to me like how the scalability model is coming into picture and what's the main, like what's the gist of the argument there.
So at what point do things become confusing? Is it how it's derived or how it's used? Is that which
I
question
mean,
you're asking?
I understand that like you define a first order approximation and you say that as you increase the system sizes, the errors would go up and they would not remain constant. But then, yeah, I think how it is used is probably the part which is not clear to me.
Oh, how it's used. Oh yes. So I mean, this goes into the details of the analysis we did. So you can pick you can pick an error correction code, you can pick an algorithm, and you have a certain epsilon accurate estimate you want to make, right? And so then there's a relationship between what errors you should get if you encode the algorithm in using the error correction scheme, right? And that and so then there's an expression about how the logical error rate looks like in your circuit, right? And that logical error will impact how accurate your scheme can be in your algorithm. So what you do is just replace the
Yeah, I
appearance.
mean, I guess like, yeah, I think I understand that. I guess like my argument is that it's probably also enough to like talk about these algorithms by just saying that like initially you will have chips that will have only like say 10,000 qubits, and it will take time for you to go from 10,000 qubits to like 100,000 physical qubits. So like you need to deal with like fixed like an upper bound on the number of physical qubits that you have, and that will essentially, like even if you assume fixed like constant error rates, the upper bound on the physical qubits will imply like how long and like will imply these trade-offs of trying to increase the number of samples by and reduce the coherent circuit size so you can deal with bigger problem sizes.
I think so the question is that where does this upper bound come from, right? Right. So you can say, oh, there's an upper bound. I'm going to say it's 10,000, but where does it come from, right? So you have to model it somehow. So if you don't like our model, you can have your own. But I've given you a model. Okay. So you can complain about I think what we call the scalability profile. You can say I don't like yours. I think these things should enter this way. Well, then you can do that, and then you can proceed with the analysis. Like, so what I'm interested in is the framework. You can replace the error correction with some other error correction scheme. You can replace the power law with some other power law scheme, all right? And then come up with your own conclusions. But the point here is that here is at least a way to think about, where this quote unquote upper bounds come from, right? So in our case, there is an upper bound that you can get, but it's motivated by something you can actually also measure from the engineering problem.
Okay. Sasha?
Yeah, hi, thanks for the nice talk. I'm Sasha. I'm a PhD graduate from Markus Müller's group in Aachen. And I have a question regarding the second plot you showed, the physical versus logical qubit. Yeah, this one. So if I understand it correctly, you're only considering a quantum memory here, right? You don't, it's only how many physical qubits do you need to encode this number of logical qubits, right? So my question would be, did you also think about how circuit depth for any like very specific concrete algorithm come into play? If you do gates, if you do the actual computation, how big of a code or how large of a code distance would you need to run like a real useful quantum algorithm, whatever that means?
Yeah, so so we do make some headway into that precise question. I didn't show the plot here, but there are plots where we're considering phase estimation, and we model the errors in the controlled operations that you have to do, and then we show the reduction factors in the depth of the circuit that you can have with these algorithms, and then talk about the same kinds of things about logical error rates and things like that. So I just didn't show the plot. Of course, you can look at the paper and see to what satisfaction we were able to answer the question. but there is a discussion about how, you know, the errors will, the scalings will go in some concrete algorithm. And that's kind of where this RFE square comes in. We're considering a specific algorithm.
And what distance is this RFE algorithm?
What distance?
Yeah, what distance?
So I mean, the RFE allows you to choose the depth. So you can fix some accuracy, and then depending on what depth you choose, right, it's gonna tell you what logical number of qubits you should use and thing. I just didn't show. I didn't want to bury the talk in minutia, but
yeah, I'll have a look at the paper. Thanks.
Cool. Do we have any other questions?
If I may.
Please.
Hi, this is Edo Justo from University of Naples. In your model, can you take into account like correlated errors that may happen due to, I don't know, cosmic rays hitting the chip? So like a bunch of qubits collapse all at the same time, basically.
Okay, a bunch of qubits collapse at the same time. Yeah. So we had very long discussions, Peter and I and the whole group, about this thing. So there's the subtlety here that I haven't talked about, and we kind of mentioned in the paper. So you know, the threshold theorems. What's the setting for the threshold theorems, right? Threshold theorems have a quantum system, right? HS. There's a bath. Then there's an interaction between the system and the bath. Okay, and so if you want to prove the threshold theorems, you try to make the interaction with the bath as general as possible, right? And then as you make the interaction more general, right, then you can prove the threshold theorems. So in your example, I think those cosmic rays will enter what you mean by the interaction of interaction between the bath and the thing, I think. But in our case, anything that gets worse as the qubits get more and more on your chip, will just be encapsulated by this scaling law. And so it allows us to not talk about the specific details of how things go wrong. Everything that goes wrong contributes to how the scaling behaves. So with the cosmic rays, okay, maybe the surface area of the chip gets big, and so there's a high probability of if it hit, right? So that will contribute to the scalability getting worse. Right. That's the beauty of the model, is that all these things can just be encapsulated in subscaling law.
Thank you very much.
Awesome. We have time for one last question before we get to the next part. Anyone?
Prakash Murali from Cambridge University. I think there's one factor that you could add to this model which may be interesting at scale, which is, and I'm not sure how accurate this is, but at least for some of the devices that I've looked at in the past, say from IBM, there is also this issue that if you want to do gates on a larger system, you may want to kind of, increase your gate time to kind of compensate for some of these effects of noise. So it's not just like there is some dependence of the physical gate time on scale, like in certain platforms. So that could influence your overall cycle time and then kind of affect your overall algorithms runtime, right? So it kind of factors into these trade-offs that you're looking at. Maybe
so
something
you mean the gate time is getting longer?
Yes. So I mean, so the way you do a gate in a small system and in a big system can have substantial differences, right? Because you want to try to compensate for different kinds of noise that may occur. So if you just have a 2-qubit chip, it may be much easier to do that gate versus if your qubit is surrounded by multiple neighbors. So So that is kind of accounted for, like the error part of it is accounted for in the scalability, but the fact that the gate time itself is longer means that your logical cycle time is now increasing because of that, and that affects your overall algorithm's performance rate.
Yeah, so the only time I know of increasing gate times is like in error mitigation. Is that what you're referring to, or something else? This is
No, I'm not referring to error mitigation, just pure bare metal gate times.
okay, I see. Okay, that's interesting. I have to look into that. What's the intuition behind increasing gate times?
The only intuition behind it is that if you want to do a gate on a small number of qubits, then you have to account for much lesser factors physically to do that gate well. While if you have to do it in a, like, let's say in a trapped ion system, right? I may want to have a very complicated pulse sequence to account for the fact that now there are so many motional modes happening.
I see.
I need to isolate it and things like that.
I see.
Yeah.
That makes sense. Okay. Yeah.
Cool. Thank you very much. So now, before I pass it to Peter, I just wanted to say that one cool thing about this paper is that all of those plots are interactive. So if you want to play with like changing some assumptions in the models, you can go to the paper. There are like links to Desmos plots, and then you can play with that by yourself. So I think it's like pretty cool, and wanted to highlight that. Okay, Peter.
Yeah, thanks for the pitch, Miao. Great talk, Amara. So we're moving to the panel section. We have 3 esteemed guests with us. So why don't we just, each take a sentence or so to introduce yourself, and then we'll move into some panel questions. So Dee, you want to go first?
Yeah, sure. Why not? Hi, everyone. My name is Di Fang. Please feel free to call me Di. I'm a faculty member at Duke University. I'm actually a mathematician, and I work more on the fault-tolerant algorithm side. Nice to meet you all.
All right, Tim.
Hey, everyone. Thanks for the invitation. I'm Tim Menke. I'm the co-founder and COO of Atlantic Quantum. We're an MIT spinout here in Cambridge, Massachusetts, and we build scalable superconducting circuit quantum computers.
Great. And Kevin?
Yeah, hi, I'm Kevin Obenland from Lincoln Laboratory, MIT Lincoln Laboratory, and we work on quantum algorithms and quantum error correction, and we work partly on this quantum benchmarking program, which we know many of the folks from Zapata and Quantum and others.
Great. All right. Well, we have a few questions for you here. The hope is that we can transition into getting some audience questions for the panel. So to start us off, related to some of the discussion going on in the chat, I'm wondering what you all think as some of the more promising approaches to quantifying this transition from NISQ into FTQC. Anyone feel free to chime in.
Yeah, I'm happy to respond. Yeah, I think I really appreciate the effort to really find like a mathematical model of how qubit systems scale, right? And I think it's instructive on the semi-abstracted level, right, to think about, okay, how do my errors scale as the system size goes up? I'm also coming here from the hardware perspective. So although I do have a little bit of experience in quantum algorithms, I'm mostly a superconducting circuit engineer. And I think while there are certain maybe quasi-continuous metrics, right? Like what happens if I actually make my chip larger, right? There's a certain, maybe there's a certain degradation or so, and one can talk about where that comes from. There are also certain very discrete things that happen as you move through different scales. And that is something that that I would like to highlight here, right? If you have 2-qubit system, right, a 1-qubit system, you can bring in wiring from every side. If you have a 2-qubit system, well, you've just blocked off one quadrant, right, in a way. But then as you scale up the system size, let's say surface 17, so a small error corrected quantum bit, like you're really restricting the routing and putting hard constraints on the chip geometry, right? And that's I think quite hard to really quantify in a continuous way, right? And there are other things such as like, what if I want to connect multiple chiplets into one big quantum system, right? Then there is a chip edge, and before I hit the chip edge, I've not had a problem at all. Like I may have figured out how to scale up to the chip edge, but once I go beyond the chip edge, I suddenly have this issue that I need to connect two chips, which is inherently, at least in the near future, a more low fidelity process, right? And so I think one piece from the hardware side here is like how do we account for these discrete effects? And that's actually something we think about a lot, and I think one can go arbitrarily deep in that. And I think one consideration is here, how deep can I go in the device model? Because at some point I will have to talk about the specific requirements of the specific architecture that I have that I've picked.
Yeah, great perspective, Tim. Thanks.
Yeah, I actually was thinking. Yeah, I
Oh.
was actually thinking something very similar, and I was maybe just summarize what the way I was thinking about it is this notion of scalability, right? So you talked about scalability with respect to errors, but then scalability in terms of the size of the system you can build, and sort of the architecture has to change, as Tim explains, as you get to larger and larger systems. But it's also it's not just the quantum architecture, but it's also the control architecture, right? It's fundamentally different as you go to larger and larger scales. And so I would encourage you to sort of think about those scalability issues too as we go to larger systems. And then I guess I maybe wanted to talk a little bit about this this middle ground, this third approach with respect to well, first of all, saying, well, for fault-tolerant quantum computers, we don't always assume that the fault-tolerant quantum computer is perfect, right? We assume that it can reduce the error rate, and we have some maximum size computation that we can do. And in many cases, it's fine if the thing fails at some rate, right? Just as long as it's not too large, because it's very easy to check our answer, and we can run it over again. So I guess what I was sort of hearing from Amara's talk was that if we want to push that to sort of some limits, further beyond something that's further push that, and what's that trade-off when we start to do that. So that's one thing. And then the second thing is, like, I'm sort of thinking about the work from IBM where they this zero noise extrapolation type work, and the question would be, is one of these intermediate sort of quantum computers something where it's still very noisy, but we understand the noise very well, and we're able to either mod it out or extrapolate our answers based on our understanding of the noise in such a way that allows us to deal with more noise than we would instead of just asking a fault-tolerant quantum computer, oh yeah, did you give me the right answer or not? Or a NIST system saying, okay, well, I'm just going to sample many times and so forth. So this notion of trying to understand the noise and use that as part of the process of interpreting our results and so forth. So I think that's another aspect of these intermediate type systems.
Yeah. Okay.
Maybe let me just say something from the fault-tolerant algorithm side, I guess. So I think the current notion of early fault tolerance that the algorithm people are trying to use, such as Peter and Amara in the paper, is that the notion primarily we consider is the circuit depth is very short. So I was just wondering whether you would think, say, from a hardware perspective or architecture perspective, this is the maybe the relevant or maybe the best way for us to consider. I think another relevant thing is that I think sort of related to what Kevin just discussed, even if we have fault tolerance, there might still be some small errors that can be generated with small probability. So I think in the algorithm community, people are also very interested in, say, for a particular task, a very well-defined task, say if I want to estimate the ground energy and if I want to do the dynamics, for this specific task, can we make our algorithm robust in certain in certain ways. For example, in this early fault tolerance quantum phase estimation algorithm, we can make things robust to the spam errors, which are state preparation errors and measurement errors, but may not necessarily be the type of errors, I think, maybe from a hardware or architecture perspective, you want us to make it robust to. So I was just a little bit curious, like in terms of the circuit, that like what would be a good notion for algorithm people who work on fault tolerant algorithm to try to get closer to the early fault tolerant that maybe sort of hopefully we can bridge the gap in. I'm just curious. It's not a comment, I guess it's more of a question.
I'm gonna let the panelists discuss that. That was basically a better rephrasing of the next question. So thank you.
Yeah, I just recognize that too. So
yeah, I would love to jump in from my perspective here, and thanks for bringing this up, Dee, and also very good to meet you. So I think like there's a lot to unpack, and number one is low probability events, right? Cosmic rays came up earlier, and the group research group at MIT of William Oliver that we spun out of has studied cosmic ray events for the they were the first ones to study that in superconductor circuits, right? And essentially they're really, really, really bad, right? And we will talk a lot about them probably in the 2030s. Like if this field moves forward as we hope, right? At some point we will get to an error rate below 10 to the minus 6, right? That's probably where this will kick in, where you can now run longer algorithms, right? And I would second Kevin's point that my understanding of fault tolerance is always that it's a certain suppression of the error. We will never suppress all of the errors. The question is how many zeros are there before the first non-zero number, right? Cosmic rays can be catastrophic partial chip failures. So they are highly correlated events, right? Like that's the thing about most error models for the surface code assume that they're mostly uncorrelated, right? You can add in some correlations back in, and Kevin is the expert in that. But once I have one of these cosmic ray events, like all the qubits on that side of the chip just die. And I have made a logical error, and there's really nothing I can do about it rather than repeating my algorithm. And I think one thing that the hardware community has to work out here is really how to protect against those errors. Like, is there something we can do from the algorithm perspective? Maybe, but I think it's probably more on the hardware side that we have to figure out how to get rid of these broken Cooper pairs that are generated in the chip, or how maybe we need to put our quantum computer into an underground tunnel or into a salt mine. Like, that's something we'll have to figure out down the line. In terms of the error models in general, I think there's a lot to do. I still don't quite know how much we can squeeze out. Like my hope is that while we reduce the error rates, and here our hope is that as we increase the size of the processor, we will actually start decreasing. Like maybe the errors go up a little bit first, but then we need to bring them down again below where we were originally, right? Because realistically, we need to be at 10% of the error code, surface code threshold or whatever your algorithm is, right? So there's a lot of back and forth there as well. That's hard to capture in the model. But in terms of error models, my hope is that we give you data, right, on these are the errors and this is their correlation, and then you come up with better models that will push up the threshold a little bit. I'm not expecting an order of magnitude, but every few percent will actually make a difference in reaching a useful fault-tolerant regime.
So maybe one more comment on that. I mean, I think there's two areas here. One is in the design of the quantum error correcting hardware, right? So the errors other than cosmic rays are probably very well corrected by surface codes and localized codes and things like this. But once you start to get to these things, as Tim says, are very correlated and knock out a large portion of your qubit, and that's very, very bad for surface codes. And so, do you design, another code or use different codes that'll help with that, or is there some way in the algorithm that you can deal with it? And I don't know how to do that in the algorithm. It seems like at the surface code, at the error correction level, this is very similar to bursty errors and things like this that people deal with in classical codes and so forth. So maybe something like that could be a useful thing.
Actually, Kevin, can I push you, or maybe Tim as
Sure.
well, to connect back to Dee's question about the like, is aiming for shorter depth circuits, is that really, the right target, or are there some other things that might be better motivated by the hardware?
Well, I mean, always reducing the depth of circuits or the number of gates in a circuit, or optimizing that, is always better, right? So when you say shorter depth circuits, are you trading off the depth for something else, or are you just trying to say we're just trying to optimize them the best we can?
Yeah, D, what?
Yeah, that's to D. Sorry.
Yeah. I think both ways. Maybe, for example, in the quantum phase estimation, if our target is the Heisenberg limit, and then which is the total evolution time is 1/procedure, and then we within this framework, what has been done was people try to make the circuits as short as possible. At the same time, there are also people interested in what if I treat the error rate a little bit higher, and I can further reduce the circuit depth. So I think both directions. There are a lot of people working on it. Peter, is that?
Yep.
Yeah, that's good. One comment I'm sorry,
yeah,
go ahead, Kevin. I was going to say, and maybe this is a little bit different, a topic a little bit, but I think I like the idea of not just thinking about fault-tolerant quantum computers, because I do like to think about fault-tolerant quantum computers. I would say that, but in that realm, what we're trying to do is we're trying to build a logical qubit, right? And this is, I know, something that Tim thinks about a lot. Is like, okay, we're going to build this in 3, 5, 7, 9, right? And all of our resources are towards building that thing. But the nice thing about NISQ, which hasn't really been as successful, is we're trying to think about different ways to use a quantum computer. And I think if we can extend that to the area where we have better qubits, I think that's a commendable thing. So.
Yeah, and indeed, like, the thing we are thinking about is how do we build this larger scale error corrected qubit, right? And the nice thing about the like grid way of encoding of encoding logical qubits is that, well, we just want to get you that device in hand, and for people to just try out, because then it will be on the user to say, well, I may want that many distance 7 logical qubits, or I want less distance 13 logical qubits, right? And I think a lot of that will be trial and error, like trying out and throwing different procedures and algorithms at it, and seeing like what is the effective logical error rate that I need. And actually, that's one point in Amara's talk about the 2014 paper, which was when I was just learning about quantum computing. It says the gates are at the surface code threshold, and yes, in a way they are. However, I think what we've learned in the last few years is really that if you look at the effective error rate in your quantum processor, and that is really an experimental metric that you will find that your effective error rate is higher than you would naively assume from just putting together all of the errors. And I think that is something that we've now found, courtesy of Google and Honeywell and others, and that's something, and ETH Zurich, something we have to take a hard look at and see how do we get that back down, right? Because people were quite optimistic when seeing these results, but that was a 2014 paper, right? And now we're here in 2024. So there's really a lot to be done. Our angle is to use better quantum bits that are longer lived, have higher gate fidelities, better readout, right? But there's really a lot that comes together in determining that effective error rate.
Okay, so this is a little bit related to the last discussion, also related to the comments that Tanuj was sharing in the chat. I think one maybe criticism of this particular model could be like, hey, should we just be using number of physical qubits as the transition parameter, the parameter to track through the transition? So yeah, wondering, I guess both from the algorithm side, the hardware side, if there might be some alternative ways to model this transition that you think are more useful from the algorithm's application or more relevant from the hardware.
Are you saying
that doesn't
number of
know.
physical?
Great.
No, number of physical qubits as a metric to when we are leaving the NISQ era, or what do you mean by that? I'm sorry.
Like to track progress.
Track progress.
On computers.
I think I do
No.
have an answer, but I think I'd also like to really hear the algorithm perspective here. So for my metric, and I think it's one of the harshest metric you can apply is what is your logical error rate, right? Take your whole device and turn it into one logical qubit. What is that error rate, right? And does it scale exponentially as you increase the number of qubits? And I think that is something that is just incredibly hard to fake, right? Because there are a lot of things like quantum volume that you can, like if you work your way around it, like you can, like everyone comes up with a new metric, but the effective logical error rate is something that is extremely hard to kind of wiggle your way out of, and then you make the code distance smaller, and you show, and now each of my individual patches has an error rate that is okay, exponentially larger, but still very small, right? And that is a way to actually characterize your system and show how deep in the fault-tolerant regime you are.
Yeah, and I'll just add something to that. Is like if you look at the different types of different architectures, like IBM versus Google on the superconducting side versus ions, right? More qubits doesn't necessarily mean better logical performance, because your connectivity is going to be much different in all those cases, and so at the end of the day, they may not give you a better performing device and so forth. So I do like that metric better as a metric for how we're doing than just raw number of physical qubits, right?
And Dee, anything else to add?
I would personally think it would be also logical errors, but I think it might be interesting to see again for the specific computational task, very well defined, and then for this specific early fault-tolerant algorithm, and what is, say, the expected algorithm error versus what is the expected logical errors. These were, I think, instead of generically say that this is, I think maybe a specific task and a specific, that.
You're saying to like go a layer higher in the hierarchy than just logical error rates.
Yeah, perhaps. Yeah.
Well, we have to wait for one logical qubit from Tim first before we can build a large algorithm.
On Tim.
Right? So
hurry up.
Counting on you.
Okay, so we have a question from Mihao or a comment.
So actually, a comment regarding metrics. So I think also like an interesting metrics that Microsoft proposed. So they haven't released the paper yet, but they discussed it at the kind of Quantum Week. Was this like reliable qubit operations per second? And I think it's an interesting metric because in the definition, and the best resource I have is my blog post. So I'm linking that. But in the definition, they have that this is a number of reliable logical qubits times the logical clock speed. So it already interconnects, like practicality in the terms of like how fast it is at a given error rate of those logical qubits, right? So even though the metric doesn't really have, the number doesn't take into account this logical error rate. The number is only meaningful for particular logical error rate, which I think is also like interesting take at, designing those metrics. So I'm waiting for Microsoft's paper when they actually go into detail about it. But yeah, I thought it's relevant and wanted to kind of share that.
That's great. Yeah, maybe that's something to just add about this paper. We have not, there are no considerations really of runtime. But we say that's something very interesting to consider in the future. Okay, well, any audience questions before we wrap up? Questions for the panel?
Oh, I think I saw a question about what was meant by gadget error correction. But by that I just meant if I have a let's say I borrow the language from like the early error correction papers where concatenating codes. And so you can set up a situation where let's say you use some certain number of qubits to encode a logical qubit. and you can set it up so that you can guarantee again that at most like one error occurs and it's not correlated to something else. So that little patch we have that guarantees what I just called a gadget.
And Amara, any comments on the panel discussion so far?
Oh yeah, so I was going to say one of the ways that this discussion can be complicated, my simple dichotomy between NISQ and LF fault-tolerant, is actually that NISQ computing is a time invariant concept, right? So as devices get better, you can always say that I'm doing NISQ because I'm not doing fault-tolerant. So that will complicate things.
So it's sort of a catch-all for not doing error correction. Is that?
Yeah, I think that's what's going to happen. Is that as devices get better, they'll just say we're doing NISQ stuff, and then once you begin to having enough error correction cycles and doing things with logical qubits, then it'll be weird to say it's NISQ, but I think people still continue calling that NISQ. Yeah.
Good point.
Okay.
Okay. Yeah. All right, Michal. I hand it back to the super MC.
Yeah, sorry. Yeah, thank you. I mean, we're 10 past time, so I think it's time to wrap up. Thank you very much for the discussion, all the people involved. I think it was super interesting. I will definitely, rewatch this once again to make sure I catch all the details. So if anyone has any follow-up questions, please feel free to contact Amara or Peter or actually anyone else who might be able to answer the question. I think it's very healthy to have those discussions either here online or via emails. And yeah, once again, thank you very much. We'll try to put it on the recording on YouTube as soon as possible. And I will let you know when we organize another meeting. I wish everyone a great day and see you next time.